This is Energy and Machines example number 9, and there's two parts to it. You've got two clowns, so you've got a larger clown of a bigger mass and a smaller clown of a lower mass, and the larger clown is going to jump from here down onto this end of this teeter-totter, and when he does that, he's going to send the other guy up in the air. And the first question that they have for us is, what is the ideal mechanical advantage of the seesaw? There's some numbers that we need for this one. Primarily, we need to know the distance in. The distance in is always from the first thing that's happening. So you'll notice that this clown is jumping down on this end, and so this end, the distance in, would be equal to 2.4 meters. The distance out, that's what comes afterwards, and the distance out in this problem is equal to 0.8 meters. The equation that we will use for ideal mechanical advantage, and this is part A again, is equal to the distance in, so din, over the distance out, d-o-u-t. Our distance in is 2.4 meters, and our distance out is 0.8 meters. When you divide the two, you end up with an ideal mechanical advantage of 3.0. Once again, there's no units on this part. For the next part, it says that the larger clown exerts a force of 850 newtons. So that would be our force in, because that's the force that is exerted. And when he jumps on the seesaw, they want to know how much force is exerted on the smaller clown. So we're looking to see how much force is going to send this clown upwards when we have the 850 Newton force from the first clown going down. The equation that we're going to use for part B is relatively simple. We know that through the conservation, the force in times the distance in should be equal to the force out times the distance out. And if you remember, force times distance is equal to work. We know the force in is the 850 newtons. We know the distance in is 2.4 meters, and that comes from this side. So we're looking at the big clown. The force out is what we're looking for, so we're going to put F out, and then that's times the 0.8 meters, and that would be on this side. So we know that we don't lose any work in between the two. They should be equal, and that's why we can use the equation. If you multiply the 850 times 2.4, you get 2040, and the unit here is going to be a Newton times a meter, and that's equal to F out times 0.8 meters. Notice that when you divide both sides by 0.8, the meters will cross off, and we're left with newtons, and that's what we wanted. So the force out for this problem is 2,550 newtons. And that is the end of example problem number 9.